When a gear tooth snaps under load, the physical destruction is obvious, but the true origin of that failure usually happens months earlier, buried in the data systems tasked with predicting it. To map risk across a product's lifecycle, standard design for reliability still relies heavily on static spreadsheets. Critical stress tolerances get trapped in isolated silos, hidden from the teams who actually need them most. Because these documents can't communicate with one another, engineers are forced into redundant data entry. A design change in one file doesn't propagate, leading to conflicting revisions across departments and laboratory tests that become completely disconnected from the current design. This graphic contrasts the approaches. On the left, the legacy problem of isolated data silos hitting a hard baseline. On the right, the Magnus model maps variables onto a continuously updating relational graph, where every component, function, and validation test is an interconnected node. With this relational architecture, if you adjust a single root parameter, like increasing a target operating temperature, that input instantly recalculates and updates all connected failure modes and testing protocols downstream. A flat grid of text simply lacks the mathematical capacity to track the thousands of intersecting variables required in modern manufacturing. Without a relational ecosystem, an intelligence deficit is inevitable. Enter model-based systems engineering, or MBSE. For enterprise organizations, this has become the standard solution to eliminate those disconnected data silos. By using formal architecture languages like SysML, MBSE platforms create a unified source of truth. Mechanical, software, and safety teams can finally align on interfaces and constraints within a single shared environment. But these systems have a limitation. They are purely descriptive. They map what the system is, but they do not actively execute the design. Because the model is passive, humans still have to interpret it. Engineers must manually extrapolate risks, author static FMEA documents, and hold lengthy review board meetings to resolve conflicting constraints between departments. This poses a strategic dilemma. How do engineering leaders transform these static architectural maps into active, self-optimizing designs without abandoning the investments they've already made in MBSE platforms? Mapping complex architecture flawlessly is essential for compliance and clarity. However, mapping a system is not the same as actively testing, negotiating, and mitigating its risks in real time. Most successful implementations use a dual-layer strategy, keeping the MBSE platform as the architectural record while adding an AI execution layer directly underneath it. The top layer, your MBSE platform, pushes structural requirements down. The bottom layer, Magnus AI, uses those models as strict boundary conditions and pushes validated FMEA evidence back up. Operating within these boundaries, autonomous component agents negotiate multi-domain constraints in seconds. The AI layer doesn't author native SysML diagrams. For formal enterprise compliance, keeping your MBSE tool of record is non-negotiable. By wrapping an active AI execution engine around a descriptive model, you create a closed-loop digital thread. The architecture model becomes a living, risk-enforced design that physically prevents late-stage validation failures. To understand how this works in practice, we need to look at how the active AI layer bypasses the manual labor bottleneck of drafting failure networks. This image shows the synthesis process. Provide a simple system context description, and the AI instantly synthesizes the required input signals, expected outputs, control factors, and noise factors. A documentation process traditionally requiring weeks of manual extrapolation is condensed into hours. With the parameters established, the system shifts focus to dynamic failure prediction, drafting actionable risk items that automatically adhere to AIAG VDA frameworks. This graphic illustrates the AI Spark processor analyzing the parameter diagrams to generate these risk proposals. It autonomously drafts failure mode items, like wire fatigue or seal hardening, based on the system logic. By automating the repetitive generation of standard risk rows, reliability engineers are elevated from data entry clerks to strategic design architects. Shifting from a document-centric workflow to context-aware intelligence generates a specific economic return. We can see this measured in a real-world application. Consider the Aerator Pro case study. This was the development of a complex premium appliance operating under strict FDA, UL, and water ingress constraints.
Over a 12-month longitudinal study, total system risk priority number dropped from a baseline of 2,225 down to 1,029, a 54% reduction. Achieving 13 full design loops in a single year dramatically outpaces the industry norm. This velocity allowed the team to run dual-axis optimization. Upgrading materials increased the per-unit cost slightly, but it slashed warranty exposure so significantly that it generated a six-figure net profit boost. Embedding real-time FMEA enforcement into every design iteration moves beyond passing compliance audits. It directly improves the economic viability of the entire product line. The system achieves these risk reductions by relentlessly prioritizing system-level impacts over what is convenient for the engineering team. It does this using a gap detection algorithm. The AI systematically scans the design and proactively flags high-severity failure modes that lack an associated physical laboratory test. For example, when the frother experienced a seal failure at 80 degrees, human instinct was to tighten the assembly torque. The platform, however, cross-referenced the materials and identified a fundamental material chemistry mismatch rather than a manufacturing error. This dashboard forces a closed-loop resolution. To mitigate the risk of shaft seal leaks, it generated an engineering change notice to upgrade the material. Rooted in empirical physics rather than guesswork, the revised design easily passes regulatory testing on the first attempt. By maintaining total situational awareness across the bill of materials, requirements, and regulations, the AI actively prevents teams from making isolated compromises that hurt the final product. For engineering directors looking to modernize, the choice between these systems depends entirely on your organizational maturity and your primary deliverables. This decision tree maps the two paths. You have to weigh pure descriptive MBSE against adopting an integrated AI execution layer. If your organization is early in its digital maturity, or your mandate is strictly to produce static SysML documentation for a defense contract, you should stick to pure descriptive MBSE. However, if you are building highly regulated, safety-critical systems and struggling with late-stage validation failures, you need to introduce an active AI execution layer to manage the cognitive overload. When your architecture scales from 20 parts to 2,000 parts, relying solely on human working memory and manual review boards becomes a severe liability. The AI platform does not replace human intent or the structural discipline of MBSE. It acts as a continuous force multiplier that enforces your engineering standards at every level. Ultimately, this technology forces a behavioral shift for engineering teams. Compliance and risk reduction can no longer be treated as an audit chore, executed only after the design is already frozen. This graph visualizes the ultimate realization of the digital thread. It proves end-to-end traceability, showing a single, unbroken chain from a base requirement all the way down to a precise laboratory test. Traditionally, FMEA is a retrospective record, a static document produced at the end of a project to answer the question, what went wrong? In this context-aware environment, the analysis moves forward, identifying which specific change will maximize safety margins before a single part is built. The era of manual, document-centric reliability engineering is ending. Organizations that transition to living FMEA-enforced designs will hold a massive